that we've been talking about all year long. And we started kind of globally and brought it back to the local level. So we're going to do the same thing here, but with regards to specifically nitrogen and phosphorus or nutrient pollution in the Chesapeake Bay. I'm not sure how far we're going to get today. But I want to give this concept and show how we're going to tie in what happens in this region to what's happening in the Chesapeake Bay and how we use the water resources modeling that we've done in this class. So where do we get water from? How much do we have? Where does it go? What happens to rainfall? What happens to stormwater runoff? How do we model that? How does that all relate to the water resources that we have and then value in the Bay region here? So we'll kind of look quickly here at the nitrogen cycle, nothing earth-shattering here. So we're going to have nitrogen and phosphorus neutrally and cycling through the environment. And like many of the things that we've talked about in our fundamentals of sustainability class also, we talked about how the Industrial Revolution, after that, during that time, we also have this nutrient revolution that many people have talked about, where we begin to use heavy fertilizer use, nitrogen and phosphorus, for crop production. And that's resulted in a lot of really great things and is absolutely necessary. But we've introduced this non-natural cycling of nitrogen and phosphorus into this environmental cycle. And that's done a lot of good things. So one of the things it's allowed us to do is to feed 7 billion people that we couldn't do before the nitrogen and phosphorus increased agricultural production. Okay? So as we look at that nitrogen and phosphorus use, we want to come up with a balance of use of the nitrogen and phosphorus to meet those agricultural needs, but also look at the consequences of use and how we try to manage that and model that and understand it from an engineering perspective as well. So we want to deal with the balancing these increases in population, the animal and energy production that we talk about, pollution levels, water, soil, and air quality issues as well. And we can see from this graph how we have different things changing, where we have human population changing over a couple hundred years, CO2 deforestation changing over several hundred years, and the fastest increase of all is actually in that nitrogen production rate. So we think about changes in land use, changes in fossil fuels. Those changes are actually much larger time periods than this change in nutrient use that we see where we go to industrialized fertilization. So we're talking about a very, very rapid rate of incorporation of these nutrients into our life cycles and lifestyles. And this is a flow diagram just like you'd see for a life cycle analysis process, where we're going to start with raw materials, manufacture those raw materials in different ways in terms of fertilizers or nitrogen and phosphorus supplements to soil, apply those to the soil, and then we tend to get into these kind of brownish lines where we have the excess nutrients that aren't utilized in the production of the crops and fertilizer, and they end up having environmental consequences downstream of the production process. So when we talk about sustainability, we want to look at how we get the maximum use out of those raw materials, right? Is there a way to maximize the use of those raw materials to turn some of these arrows that go one way into a net negative thing into a positive, into being able to recycle, reuse those materials, or use them more efficiently in the process? And a lot of the environmental regulations that we'll talk about that are happening in the Bay Area right now and are being implemented in the Bay Area right now are based on that application and utilization rate. So trying to use this more efficiency, where we change the weight of those lines so that we have the same lines going into the process, but we have thinner lines, right, making less mass going out of those processes in terms of waste processes. So when we look at this, because of population, because of food demands, because of economic growth, people wanting higher protein foods as well, shifting from a vegetable diet, rice diet, to more protein-based diet, all valuable things in terms of health and nutrition. we expect to see greater demands even going into the future in nitrogen and phosphorus use. Not the same rate as population change, but we continue to expect increasing demands, although there's a range on that, just like there's a range on everything. So the main threats that you can think about as we talk about the nitrogen and phosphorus threats are really water quality threats related to freshwater dead zones, eutrophication processes, air quality issues. This also is going to relate into climate change, the greenhouse gas balance, and I'll make these notes available to you, so I'll give those to you in full so you don't have to write with pens. You're welcome to if that helps you learn, but you don't have to. And then all those things, of course, the environmental quality concentrations of things in the environment are going to influence biodiversity within an area. And we'll also talk about soil quality, which is going to be really important too. So a couple graphics that sum this up, and one of the junior groups did a really nice job of finding this graphic, which I really like, which identifies nitrogen loading. So and what we want to do through this process is come up with the ways to quantify this. So qualitatively, we can talk about these threats from nutrient pollution, but we want to come up with quantitative means to model this system. So what are those arrows? What are the levels in which we have negative biodiversity, increased algae blooms? How do we model that? And then going beyond the models, how do we actually control that and manage the system, that nitrogen phosphorus system that I just showed on the previous slide? How do we manage that system to reduce these negative impacts to the system? I've tried to focus this discussion on the Chesapeake Bay. This just to note that there are many, many areas of the world, many high population areas of the world, whether it's President Obama talking about the Everglades, talking about Puget Sound, where that last graphic was from, talking about the Gulf of Mexico and the Mississippi Delta, talking about water quality in Europe or Southeast Asia. Okay? This same fundamental engineering processes are going to apply to any of those particular locations. So the word nexus seems to be in vogue here, so people use it with regard to the nutrient nexus as well. But really talking about the intersection of these things and managing this complex system, which highly is dependent upon water quality in this particular system. So this is a nice schematic which tries to tie some of these concepts together, where we're looking at raw material usage in terms of nitrogen and phosphorus supply, along with other nutrients that may affect crop growth and food production. So the food production is going to be driven by the human-centric demands of human population and consumption, down in the yellow on the bottom left. And then we have these threats for the excess nutrients, where we have too much nitrogen and phosphorus influencing air and water quality. Our goals that we want to influence as engineer are on the far right-hand side, where we're trying to balance cleaner environment, greater food security, better water security, reduced climate pressure, better health and sanitation. Right? So we're trying to do all these things in managing this cycle of nitrogen and phosphorus. And this is going to be really one of the great challenges that are going to put demands upon the engineers who are comfortable working with networks, working with systems, understanding these complex relationships, but understanding them in a way in which they can apply the quantitative processes of engineering the mass and water flows, and understanding those from a quantitative standpoint to be able to make engineering decisions as to how we manage those resources. So a couple quick definitions that we talk about. So we're going to talk generally about nutrients. So in this talk, I'm going to be talking specifically about nitrogen and phosphorus. Plants are going to require other nutrients as well. But when we talk about nutrients in this presentation, we're going to really be focusing on nitrogen and phosphorus and the utilization of those things, both in waterways and then for agricultural purposes as well. So when we talk about agricultural purposes, we'll talk about here different terminologies. So we want to fertilize something, we want to add the right mixture of nitrogens, okay, that can be nitrogen, phosphorus, but also some of the micronutrients, so the right balance of soil ions as well, so that the crops can grow at their maximum production rate for a given area of land. We can maximize both food production, economy, and reduce energy input by maximizing food production. Those are all positive things, right? Typically, we talk about fertilizer. Fertilizer is a substance that contains these nutrients. I'm going to be breaking the term fertilizer down a little bit, where if I'm talking about fertilizer, we're going to talk about fertilizer in terms of particularly urban use. It can also be large agricultural scale use as well. Fertilizers are used as well. But when we talk about fertilizer use here, in this particular area and in this region, we're going to be talking about the particular fertilizer that comes from animal waste, okay, and that's manure. So we'll talk about manure and how that relates to animal production, because that's a byproduct of animal production. So we'll look at some of the specific numbers that relate to that in this county, right here where we are in Rockingham County as well.